Hey guys, welcome back to another lecture video for Chem 115. In this video, we will go ahead and take a look at how to prepare buffers by determining how much volume or how much mass of a specific substance should be added to a solution. Now, these substances that we're adding to the solution can either be a strong acid or a strong base or a conjugate acid or a conjugate base. And what's going to drive us to add one substance over another just really depends on the composition of the solution that we have. So that way we can transform our current solution into a buffer. And so we're going to look at four examples for 4 word problems that we're going to work through. And hopefully by the end of this video, you guys get a strong sense of how to tackle these types of problems. And hopefully you guys can be inspired to prepare your own buffer in the near or far future. All right, so let's go ahead and look at the first example. A student wants a buffer solution at a pH of 8.580. Okay, so we have, so here we have a target pH of 8.580. And so currently the student has 1.5 liters of 0.400 molar concentration of ammonia. And so the question is asking how many grams of ammonium chloride needs to be added to the solution. And so the Kb of NH3 or ammonia is 1.77 times 10 to the negative 5. And so when I personally tackle word problems, I like to visualize what's happening. And so I'm going to go ahead and take a step back and kind of draw or imagine what this question is trying to describe. So if I were a student and if I have 1.500 liters of 0.400 molar of ammonia, I would go ahead and draw something like this. Okay, so notice I have my concentration, I have the identity of the substance, and I have the volume for that specific solution. And so the question is asking us how many grams of ammonium chloride do we need to add to create a buffer that has a pH of 8.580. Okay. And so before I start going into the calculations, I want you guys to go ahead and take a look at the components inside the beaker. Notice that we only have one substance, which is NH3. And so even though NH3 is considered a weak base, it alone cannot act as a buffer. And so for us to create a buffer solution, we need to add its conjugate acid. And so this is the reason why this student is adding ammonium chloride. And so if you guys look at the chemical formula of ammonium chloride, it is NH4 plus, NH4 Cl minus. I think in my head I'm trying to dissociate this. And so if I just continue on with my thought process, if you're putting this in water, and if this is, for example, a solid, this ammonium chloride is going to separate to produce ammonium plus and chloride minus. Okay. And so this is going to be aqueous, and this is going to be aqueous. Now, based on previous lecture videos that I've kind of made, and hopefully you guys have watched, we know that chloride will not affect the pH of the solution because it is simply an anion of a strong acid. So we can go ahead and ignore chloride from here on out, probably except we'll revisit this chloride once again in the last part of this calculation. But in terms of just the general concept, we can go ahead and ignore chloride when it's aqueous in solution. And so really the active component of, if you will, of ammonium chloride is ammonium. And ammonium, if I write it down here, is a conjugate acid of a weak base. And so by adding ammonium into this solution, what we're creating is a buffer. Okay. And so how do we calculate this? How do we quantify the mass of ammonium chloride that we need to add? Do we just take a scoop and just kind of hope for the best? Or is there a more exact method to determine this value? And so to do that, we're going to go ahead and revisit the Henderson-Hasselbalch equation. I'm going to go ahead and use the pH form of Henderson-Hasselbalch's equation. And I've already added in where ammonia and ammonium is supposed to go. And so if you recall, the base is going to be in the numerator in this form of the Henderson-Hasselbalch equation, and the acid, or HA, it's going to be in the denominator in that ratio, in that fraction. All right, and so I'm going to go ahead and once again revisit this bracket. And so this bracket is representing molarity. And we know that molarity, I'm just going to duplicate this for completion of my notes. And so molarity is moles per liter. And so if you guys are looking at this Henderson-Hasselbalch equation, this equation can actually help us determine the number of grams that we need to add to this solution to create our buffer. And so what do you think the connection will be? How do you think we can use these units that you guys are seeing on the screen to go from, to get us into the mass that we need to put inside the solution? And so if you had said moles, then you guys are absolutely correct. And so if you guys recall from the first semester of general chemistry, moles can be converted to grams, which is something that we can physically do in lab by using the molar mass of that substance as a conversion factor. And so just making this realization, the fact that moles will get us to grams, kind of gives us a goal to work towards. In other words, if I can get the moles of ammonium by using this Henderson-Hasselbalch equation, then I can go ahead and use molar mass as a conversion factor to express that value in mass units, specifically grams. And so the question now comes to be, how do we express this bracket into moles? And so if you guys are looking at the Henderson-Hasselbalch equation, specifically this fraction form, since we have a ratio of two molarity values, so here I have NH3 molarity over NH4 plus molarity. If I convert each unit into its definition, in other words, moles per liter, divided by moles per liter, I can go ahead and cancel out volume and just express these values in terms of moles. And so if I can figure out the moles of ammonium, then I can go ahead and determine the mass. And so what that means is that I need to convert all units into mole units before we plug it into the Henderson-Hasselbalch equation. Okay. All right, so hopefully you guys kind of understood my train of thought. Sometimes it kind of helps to work backwards and be able to like break down the units to help me develop a solution map. Okay. And so we want to convert everything into moles so that we can plug it into the so that we can plug it into the Henderson-Hasselbalch equation. And then we're going to solve for moles of ammonium. And then once we have moles of ammonium, we're going to go ahead and use the molar mass of ammonium chloride to convert it into gram units. So let's go ahead and do that. According to the problem, we have 0.400 molar concentration of ammonia, and the current volume is 1.50 liters. And so if you multiply these two values, the value that we're going to get the value that we're going to get is in mole units. Okay. So we're going to take 1.50 liters of ammonia, and then we're going to go ahead and multiply it by 0.400 molar. And so I'm going to go ahead and convert molarity into moles per liter. And so that'll allow us to cancel out the volume. And if I were to multiply across, the number of moles that I would get is 0.600 moles of ammonia. Okay. And so if I'm going to rewrite the Henderson-Hasselbalch equation, I'm going to go ahead and put that 0.600 moles in the numerator. And that is for ammonia. And what we're trying to figure out is the number of moles of ammonium. Okay. And so before we can figure that out, we need to plug in a couple numbers. We need to plug in pH. And we need to determine what the pKa is of the solution. And so the pH is already given to us in the problem. It's 8.580. Okay, so I'll go ahead and write that down. .580. And so to determine the pKa, I need to look at what value this problem gave me. It gave me a Kb of ammonia. And so since that value is Kb, I cannot plug it in just yet. I need to convert Kb into Ka. And so I'm going to go ahead and just kind of do this off to the side here. So since my Ka is equal to 1.77, I'm sorry, that's not my Ka, my Kb is equal to 1.77 times 10 to the negative 5. I'm going to use the relationship Ka times Kb equals to Kw. And so I'm going to go ahead and divide Kb over so that I get Ka is equal to Kw over Kb. And once again, we're going to assume that we're at 25 degrees Celsius. The problem didn't state otherwise. So Kw is going to be 1.008 times 10 to the negative 14 over 1.77 times 10 to the negative 5. And so therefore the value of Ka is going to be, if you plug that into your calculator, it's going to be 5.6949, and then a whole bunch of other numbers, times 10 to the negative 10. Okay. So this is telling us that the magnitude times 10 to the negative 10. So ammonium is a very, very, very weak acid. All right, and so to determine the pKa, we're going to take the negative log of the Ka. And so I'm going to go ahead and plug this guy into here. And so let's talk about sig figs real quick. Here there are 3 sig figs, and so I'm going to go ahead and highlight the first 3 significant figures that I see, just to remind me of how much I'm supposed to record. And so my pKa, if you plug that into your calculator, so negative log of 5.6949, et cetera, times 10 to the negative 10, that's going to give us a value of 9.2445512, whole bunch of other numbers. And if you guys remember when we're taking the negative log of something, we have to report the correct number of decimal places. And so since we have 3 sig figs, we need to report 3 places after the decimal. And so this 5 is going to round that value up to 9.245. And so this is going to be the pKa of this solution. And so I'm going to go ahead and replace that. Okay. All right. And so from here on out, this is just algebra. What we're going to do is we're going to subtract this to the opposite side. And when we subtract 8.580 by 9.245, we're probably going to get a negative value. And so if you plug that into the calculator, we get negative 0.66451, and then a whole bunch of other numbers. And then that's going to equal to the log of 0.600 over x. Okay, so I'm just bringing that down. And so here in this case, for sig figs, since we're subtracting these 2 values, I probably would just want to report 3 places after the decimal. And then I'm going to go ahead and take the base 10 of both sides, and I get 0.60 over x. And the value that I'm going to get is going to be 0.216514. And so to solve for x, and then there's a whole bunch of numbers, to solve for x, we're going to switch the position. So we're going to cross multiply, if you will. And we're going to punch in our calculator 0.60 over 0.216514. Okay. And so when we divide these two, the value that we're going to get is 2.77. Now this x represents ammonium. If you recall, but more specifically, it represents the moles of ammonium. And so we're going to go ahead and put moles of ammonium here to remind us what this x is representing. And so this is cool because now that we have, moles of ammonium, then we can go ahead and convert it into grams of ammonium chloride. And so we're going to perform some stoichiometry here, some dimensional analysis. So 2.77 moles of ammonium. And since I want the original substance, right? So the stock bottle doesn't have ammonium exclusively. The stock bottle has ammonium chloride. So you have to use both substances. Even though we solved for just moles of ammonium. And so we can go ahead and do a mole-to-mole relationship. For every 1 mole of ammonium, that's equal to 1 mole of ammonium chloride, right? So if you look at this chemical formula, for every 1 of this chemical formula, there's 1 ammonium. Okay? So that's where I got that 1-to-1 relationship. And then now that I'm in moles of ammonium chloride, I'm going to go ahead and calculate the molar mass. So I'm going to use the molar mass as a conversion factor, and it's going to be the molar mass of NH4Cl. And so for every 1 mole of NH4Cl, that's going to give me 53.491 grams of ammonium chloride. And so you guys are going to be using the periodic table, specifically the atomic mass. So you're going to look at the periodic table, determine the atomic mass for every single one of these elements, multiply them by the quantity, so 1, 4, and 1, and then you guys are going to add all of them up, right? So you have 1 nitrogen plus 4 times the atomic mass of hydrogen plus 1 times the atomic mass of chloride. And if you add all of them up, you get 53.491. I'm using 3 places after my decimal for precision. And so if I multiply everything and divide everything, I'm going to get 148 grams of ammonium chloride. And so I'm putting only 3 sig figs because it looks like 3 sig figs is the least number if you guys are looking through this calculation. Okay. And so we did it, right? We were able to determine the amount of ammonium chloride that's present or that's required to prepare our buffer. So let's think about this concept one last time before we look at it in another example. And so if you want, and I'm going to erase this because I'm going to re-highlight it again in pink. So if you want a buffer solution at a pH of 8.580, we are going to add 148 grams of ammonium chloride into this solution that contains 1.50 liters of a 0.400 molar ammonia solution. Okay, and so in lab, if you guys have this specific concentration on hand, you guys are going to measure out 1.50 liters, and then you're going to go ahead and add 148 grams of ammonium chloride. You're going to mix it around, and you guys are going to determine the pH, make the necessary adjustment by adding small amounts of acid or small amounts of base until you hit a pH of 8.580.